So I'm going to return to the question of first best emission reduction. And I've said now a number of times that climate change is a long-term problem, that climate change is a global problem, and that climate change is an uncertain problem. A more pointed way of saying the same thing is, and I also showed you that if you just do the middle of the road parameters and you stick that into a model like Nordhaus's dive model, you don't do a whole lot of greenhouse gas emission reduction. And what I'm going to do over the next 4 hours, 3 hours, is redo this and look at how sensitive it is to particular assumptions. And the point that I'm going to try and make with this somewhat long period is that if you don't care about the distant future, and you don't care about what's happening in faraway lands, and you don't care about what happens with small probabilities, then climate change is not for you. Right? And climate change is not something that you should worry about. Alternatively, if you do care about any of these three, or all three, then climate change is something that you should be concerned about. And I'm going to start with the future, and I'm going to start with discounting. Now, we've seen this graph. It shows the marginal damage cost, essentially the additional damage done by putting an extra ton of CO2 into the atmosphere. And I told you this is kernel CDF, estimated to some 750, or calibrated or fitted to some 750 primary estimates, the social cost of carbon. And then I told you we did a sample split. And last week I said this is for a 5% discount rate, for a 3% discount rate, or for a 2% discount rate. While at the same time the graph actually showed different numbers, 3, 1, and 0. Instead of discount rate, which would be logically abbreviated to DR, I have here PRGP, the pure rate of time. So I'm going to talk about that first. At Twitter in England, there's always a lot of talk, particularly around weekends, about Ramsey. That's Aaron, who's a football player. This Ramsey is Frank, who is long dead, was a professor of economics at Cambridge and wrote a rather influential paper in 1928 in the Economic Journal. And what he derived was a rule that since then has become known as the Ramsey rule. Now, I'm not going to take you through his derivation, but I'm going to show you an alternative derivation that is easier to follow. The net present value of receiving $1 or €1 or £1 or one whatever in t years time is equal to epsilon, and epsilon is equal to e to the power minus rt. T is the distance in time, and r is the continuous time discount rate. You may be used to thinking of discount factors, this is essentially discount factor, as 1 over 1 plus r to the power t. If you let the time steps go from 1 year to 1 month to 1 week to 1 day to an hour to a minute to a second to infinitesimally small, then you would find that 1 over 1 plus r to the power t converges to e to the power 1 over e to the power rt. And that is what we see. Now, this is just a definition, right? This is the discount factor. This is what we think the net present value of $1 of receiving $1 in t years time means. The discount or the discount factor is essentially an equivalent, and it's an equivalence in utility. Essentially, it says I'm indifferent between getting $1 in t years time or getting epsilon dollars now. That is the discount factor. It's an indifference principle. So, what do we know? That we are indifferent between getting $1 now and getting $1 then, or getting epsilon dollars now, right? So we can also impose a second equation. It's essentially you're getting epsilon dollars now. So our change in utility is epsilon times the first partial derivative of utility to consumption at time 0. Y epsilon times the marginal utility is essentially the first order Taylor approximation, right? This is the Jacobian transformation. So that is how our utility would change if we would get epsilon dollars now. If we get $1 in the future, the same thing holds, right? We get $1, we apply, multiply it with the marginal utility in the future, and we care less about the future than we do about today. And that is the term that we see here, e to the power minus rho t, which is not the same as e to the power minus rt. This is not a typo. RT is a money discount. It's our indifference between getting $1 now and $1 in the future, getting epsilon now and $1 in the future. Rho t is our indifference between receiving utility now versus receiving utility in the future. So this is a pure rate of time preference, or rather a rate of pure time preference. That for historical reasons, the word pure has ended up in the wrong place. So this is how much we care about future utility relative to today's utility. So this is the definition of the discount factor in money. This is our indifference principle. The two equations have to hold together. If this is true, then we can just work out what would epsilon be. We kick u sub c to the other side of the equation. Then we introduce a constant rate of risk aversion type of utility function. So u sub c becomes c to the power minus eta, where eta is our rate of risk aversion. That doesn't fully get us there, because now we have a function in C0 and a function in CT, and the question is, what is CT relative to C0? If we assume that consumption grows by G per period, so we assume that we get richer and richer and richer and richer, that G is positive, then the difference between CT and Z0 is a factor e to the power GT. That's essentially our assumed growth rate of consumption. To raise that to the power minus eta, so minus eta ends up there. Now we're getting someplace, right? So C sub 0 cancels against C sub 0. And what we're left with is that epsilon equals e to the power minus rho t minus eta g. So that is our indifference rule. We also know that by definition, epsilon equals e to the power minus rt. Take the logarithm both sides of the equation, and we have that minus rt equals minus rho t minus eta gt. Do away with the minus signs, do away with the t, and what we have is the Ramsey rule that says that the money discount rates are equals the utility discount rate rho plus the growth rate of consumption g times the curvature of the utility function eta. That's the Ramsey rule. As I said, he derived it in a different way. Graphically, this right. So the indifference that we're looking at is we're giving up. Yeah, let's do it. So the question is how much should we not save, right? So we're giving up consumption now. We're moving slightly to the right. So this is consumption. This is utility. We're giving up consumption now. That will lead to a delta loss. In return, we're increasing consumption in the future. Will lead to a delta gain. Now, if this distance is the same as this distance, and in the meantime we have grown richer, then this is a bad deal, because the euro extra saving would lead to a large drop in utility now, but the extra euro that you would get in the future, if there's no interest rate, would lead to only a tiny increase in well-being in the future, right? So in order for the So in this graph, the horizontal distances are equal. In this graph, the vertical distances are equal. This line is equal to this line. And that means that in order to give up $1 now, we need much more than $1 extra or €1 extra in the future, right? So that is essentially what the Ramsey rule does. This horizontal line is equivalent to this line if we compare it in welfare terms. So that is the second component of the Ramsey rule. Because we expect to be richer in the future, we care less about money then, extra money then. And from your perspective, that is sort of obvious, right? I mean, you're at a pretty low income now, a pretty tight budget. Next year, you'll hopefully have a job. Your G is very large. So you'd be absolutely crazy to save now to sort of put away the little bit of money that you have now so that next year you will be a bit richer. Given your expected income growth, that would be sort of the stupidest thing you can do, right? Definitely, if you take the money to the bank and get 1% interest rate, how dumb can you be? So you guys should be spending a lot, right, rather than saving a lot. Or you should spend as much as you have rather than it should still not be a lot. So that is one reason why, if you're in a situation of rapid consumption growth, you would want to discount the future in the sense that winning an additional €10 in a year's time from now should not get you excited. This is uncontroversial, right? What is not uncontroversial is what should our G be, what should our H be, or our epsilon be, what should our eta be? It's an eta, right? That is not uncontroversial, but the principle is uncontroversial. There's a second component to the Ramsey rule, and that is rho. And rho says I'm also going to discount future happiness. So if I have to choose between becoming 1 unit happier today versus 1 unit happier in years from now, I'm going to go for the 1 unit happier today. This corresponds to what people do and how people are. People are impatient. If I give you the choice between having to wait for another 3 weeks to watch the first episode of the series of Game of Thrones, or offering it to you tonight, you would jump on tonight, right? It's just as good in 3 weeks' time, probably better in 3 weeks' time, right? You'll share with all your friends, but I sort of offer you, I can't, that's not within my power. If I sort of offer you this now, you will go for it, right? You are impatient, you want the good stuff now. And that actually pervades all our behavior, right? That we want things sooner rather than later, even if you control for uncertainty and so on and so forth. This rho is controversial because it also sort of implies that we care less about the future for the simple fact that it is the future, which in an abstract sense is very peculiar. If we sort of take any religious tract, if we take the advice of any philosopher, they would say it's immoral to discount the future. Socrates was pretty adamant about this. He's a little bit vague, but he did throw out the money changes from the temple, right? Mohammed was very, very clear about this. That usury is bad, right? You cannot discount the future for the sheer fact that it is the future. If we listen to all the great economists who have written about it, including Ramsey, including Koopman, including Harrod, they all say rho should be zero. We should not discount the future just because it is the future. It's a lack of imagination if we take Ramsey's word. I'll come back to this a couple of times. The thing that I followed in my derivation of the rule is a consumption decision and a savings decision. You could also interpret R as the interest rate that you would get from the capital market. And that is what Ramsey really did. If you sort of assume that an economy is in dynamic equilibrium, then your consumption way of looking at what should the interest rate be, what should the money rate of discounting R be, then of course that would equate to the marginal return on capital, which of course determines your interest rate in equilibrium. So if the economy is in a dynamic equilibrium, then the interest rate should equal the consumption rate of discounting R and give back in the same sort of reasoning. The implications for climate are obvious, and I'll come back to those. What enters into our calculation of the social cost of carbon is R, that is a money discount rate, and social cost of carbon is expressed in money. Indeed, R depends on growth. The more impatient we are, the less we care about the future. So that is important, but also the faster we grow, the more we should discount the future, and the more curved our utility function is, the greater the eta, and the more we should discount the future. And of course, the more we discount the future, the less we care about climate change, the less we need to do about it. So all of these three parameters are important. Okay, I'm going to continue this discussion tomorrow.